How one mechanic's simple bolt fix made a '69 Camaro outlast every other car. The transmission paired with this engine was built to be just as tough. General Motors engineered the turbo-hydromatic 400 transmission to withstand roughly 450 pound-feet of torque in its factory configuration. It used a heavy cast-iron case, a 32-spline output shaft, and a bolt-on bell housing designed to match the standard Chevrolet bolt pattern. Between the engine and transmission sat the torque converter, the fluid coupling responsible for transferring engine power to the gearbox. This converter measured about 11.5 inches across and had a stall speed close to 1,800 revolutions per minute. That detail is important because the torque converter plays a central role in what happened next. When Jim first heard the knocking noise, his thoughts immediately jumped to the worst possibility: rod bearing failure. Inside a small block Chevrolet engine, connecting rod bearings endure extreme forces. During peak combustion, each bearing can experience loads exceeding 6,000 pounds per square inch. These bearings depend entirely on an extremely thin layer of oil, usually between 15 thousandths and 20 thousandths of an inch, to keep metal surfaces separated. If that microscopic oil film disappears due to contamination, age, or oil starvation, the bearing begins to wear rapidly. At first, the clearance increases. Soon after, a knocking sound appears. If the problem continues unchecked, the connecting rod may eventually break free and punch through the engine block, a failure enthusiasts grimly describe as throwing a rod. Jim knew these warning signs well. He had spent his entire life around engines. The noise he heard followed the rhythm of engine speed. It grew louder when the engine was placed under load and carried the deep, hollow tone mechanics usually associate with bottom-end damage. Each revolution brought another metallic impact. The sound made Jim physically sick. This wasn't some worn-out junk engine. The motor had been cared for obsessively for more than 5 decades. The oil had been changed every 3,000 miles, using Valvoline VR1 racing oil. The cooling system was flushed every 2 years. The engine had even been rebuilt once back in 1987 using forged pistons and chrome moly piston rings. Since that rebuild, the engine had accumulated only 31,000 miles. So the sudden knocking noise made no sense at all. Jim's first stop was Cincinnati Speed Shop, where a veteran engine builder named Dave had been building racing engines since the 1970s. Dave listened to the engine with a mechanic's stethoscope, placing the probe at several points around the block. To him, the sound seemed to originate from the passenger side near cylinders 5 and 7. His conclusion came quickly and confidently: a spun rod bearing most likely on cylinder number 5. Repair estimates were discouraging. A basic engine rebuild would cost roughly $3,500, and that number could climb higher if internal damage was discovered once the engine was disassembled. Dave explained that when a bearing spins inside its housing, it usually scars the crankshaft journal. In the best situation, the crankshaft could be machined 10,000ths of an inch undersize and paired with oversized bearings. In the worst case, the crankshaft would need replacement entirely, adding another $800 to the bill. Jim wasn't ready to commit to that diagnosis yet, so he hauled the Camaro to another shop called Muscle Car Restoration Incorporated, a company specializing in numbers-matching classic vehicles. Their lead technician, Roberto, had more than 30 years of experience working on General Motors performance engines. Roberto began with a compression test. All 8 cylinders produced readings between 165 and 170 pounds per square inch, exactly what you would expect from a 10.25-to-1 compression engine. Oil pressure readings were equally healthy: 45 pounds per square inch at hot idle and roughly 65 pounds per square inch at 2,000 revolutions per minute. On paper, the engine looked perfect. Yet the knocking noise remained, hammering steadily as if mocking the otherwise flawless test results. Roberto dug deeper. He drained the oil and cut open the oil filter to search for metal particles that would suggest bearing damage. The oil looked clean. The filter showed nothing beyond ordinary carbon residue. Next, he removed the valve covers to inspect the rocker arms and valve springs, checking for anything that might imitate the sound of a rod knock. Everything was within normal limits. The mystery grew deeper. How could an engine show excellent compression, proper oil pressure, clean lubricant, and still sound like catastrophic internal damage? The third opinion came from Tom Bradley, a semi-retired mechanic who had worked at a Chevrolet dealership from 1968 until 2005. Tom had seen virtually everything. He had watched these cars when they were brand new, repaired them through decades of use, and rebuilt countless small block engines. Jim contacted him as a final attempt for help. Tom arrived carrying nothing more than a basic set of tools and 50 years of mechanical experience. He started the engine and listened carefully. Then he did something neither of the previous mechanics had attempted. He crawled completely underneath the running car. For nearly 20 minutes, Tom slowly moved from the oil pan toward the transmission while using a mechanic's stethoscope to isolate the source of the sound. He asked Jim to rev the engine while he listened at different locations. He inspected the harmonic balancer for vibration, checked the flywheel through the starter opening, and eventually concentrated on the bell housing, the aluminum structure connecting the engine and transmission. Curiously, the knocking seemed loudest there. That didn't seem logical. The bell housing contains almost no moving parts except one, the torque converter. Tom asked Jim to shut off the engine. Using a 9/16" socket with a long extension, he reached through the inspection opening beneath the bell housing. The Turbo Hydromatic 400 transmission attaches the torque converter to the flex plate using 6 bolts. Tom checked them one by one. 5 bolts were tightened correctly to the specified 35 pound-feet of torque. The 6th bolt, positioned roughly at the 2 o'clock position, turned freely for nearly 3 full rotations before finally tightening. That bolt had slowly backed out. It protruded just enough, about 1/8 of an inch, to strike the inside of the bell housing every time the engine rotated. At idle speed, the engine spins roughly 750 times each minute. With each revolution, the bolt head tapped the bell housing. The impact traveled through the metal structure of the bell housing and engine block, producing a sound nearly identical to a rod knock. The torque converter remained attached because the bolt was still partially engaged. But it was loose enough to create the terrifying noise Jim had been hearing. Tom tightened the bolt to the proper specification and asked Jim to start the engine again. The knocking sound vanished instantly. The engine ran smoothly, as if nothing had ever been wrong. Jim later admitted he nearly cried with relief. 3 experienced mechanics had nearly dismantled a perfectly healthy engine. Tom had solved the problem in less than a minute without replacing a single part. From an engineering perspective, the situation is fascinating. An empty torque converter in a Turbo Hydromatic 400 transmission weighs roughly 35 pounds and closer to 50 pounds once filled with fluid. At idle speed, it spins around 750 revolutions per minute, and at cruising speeds it may rotate 2,500 revolutions per minute or faster. The forces acting on the connection between converter and flex plate are significant. To prevent failure, General Motors engineers specified 6 grade 8 bolts capable of handling around 150,000 pounds per square inch of tensile strength. Those bolts thread into welded nuts inside the torque converter and are intended to be installed with Loctite 242 thread locker. The adhesive prevents bolts from loosening due to vibration. Over decades, however, that compound can degrade, especially when exposed to transmission fluid leaks or repeated heat cycles. That degradation likely allowed the bolt in Jim's Camaro to slowly loosen over time. Tom had encountered this issue several times throughout his career. During his decades at the dealership, he had seen perhaps a dozen similar cases, usually after transmission service where thread locker was forgotten during reassembly. Some customers had even authorized complete engine rebuilds before anyone thought to check those simple bolts. Ironically, modern diagnostic technology sometimes makes problems like this harder to detect. Technicians rely heavily on computer scans and overlook basic mechanical investigation. Jim had nearly approved a $3,500 rebuild. That would have required removing the original numbers-matching engine from his 1969 Camaro and tearing it apart completely, only to discover nothing wrong. Beyond the wasted money, such a rebuild would have reduced the car's collector value. A numbers-matching 1969 Camaro with its original drivetrain can be worth anywhere from $50,000 to $80,000, depending on options and condition. Even a professional engine rebuild can reduce originality value by $10,000 or more. Instead, Jim's Camaro remained untouched. The engine stayed original, and the car continued running perfectly, all because one experienced mechanic listened carefully and followed the evidence instead of assumptions. 3 years after Tom's simple repair, Jim's Camaro continues to run flawlessly and has accumulated another 5,000 trouble-free miles. Jim now checks the torque converter bolts regularly during oil changes and shares the story with other classic car owners. Sometimes the most terrifying mechanical problems turn out to have the simplest solutions. And sometimes the difference between a massive repair bill and a 30-second fix is nothing more than experience.